Okay, angular momentum. See what is angular momentum and related questions will be discussed. So, would you remember the linear momentum? The linear momentum, you write it as mass multiplied by the velocity. Angular momentum, similar way we can write it, but the definition is that angular momentum is the moment of the linear momentum. So, okay, you write it. Let's write there. The angular momentum of a particle, angular momentum of a particle angular momentum of a particle about an axis, about an axis is defined as the moment of linear momentum. Linear momentum of the particle. The particle about that axis. About that axis. That is the definition, right? Angular momentum, which is the moment of the linear momentum. So you need to know that angular momentum is a vector quantity, right? Normally the symbol we use angular momentum as a capital L. So after that you can write the angular momentum is a vector quantity. Vector quantity. Right. Right. We consider this is the axis of rotation, and from this axis I consider points the particle. Let's say this particle is moving along a circular path of radius r here, and it has a velocity, linear velocity, tangential velocity x is p, and omega is the angular velocity about the axis. Mass is m, let's say, right? Here I'm considering only one particle, single particle. Later I will discuss this for the other particles also. And the linear momentum of this particle, which is similar to similar direction, is p equals less mass. And angular momentum about this particle, like you can write then. For the definition, it is the moment of linear momentum. That's we can write this is linear momentum multiplied by the perpendicular distance. Perpendicular distance from the axis of rotation to the line of action of the. I'm not writing all, we can writing that. And this angular momentum you can write that's L. Linear momentum is P, and the perpendicular distance from here to this velocity path is R. So P you can write as mass into the velocity R, and mass we know that V equals R omega. You write R omega into R. It's gives you as mr square and so many. What is the mr square? The moment of inertia of a particle is rotating at the distance r. You can write it mr square. That's I, the moment of inertia. So then you can write that is I omega. So the moment of inertia, I here, right? Mr square. So then the angular momentum for particle, you can write it is equal to I omega. Or for a particle, we can write it as mvr also. Mvr. This is only just only one particle. Let's see, is it a whole body, rigid body or not? Later we discuss that one. First, you write up to this point. Write it down and let me know if you finish, right? Write it down and let me know if you finish, right? Right there, there's a, you can write, yeah, I'm writing here. That is psi units of psi unit of angular momentum. That's the I is measured in kilogram square meter, and the omega measured in radians per second, right? That per second only we consider, we don't need to put radians there. If you write it as radians also, it's okay. Like this. I don't need to put radius, you can write this as a units. Kilogram square meter per second is the angular momentum of a particle. Here, you consider above the rigid body. I'll go to the next bit. Okay. Right there, that's the pure momentum of a rigid body. let's say they're having a body like I'm going to get the angular momentum where this axis passes through this point. So let's see this body is rotating about this axis. The mass of the body I'm considering in not if rigid body we consider. And it's rotating with the angular velocity omega, let's say. And you know that's this body composed with different that's particles. Okay? I'm considering these particles there. When this rotates, the body is rotated to this side. So all particles have their linear speeds. It's V1, V2, like Vn. And the distance to these particles in the axis of rotation is R1. You can say this other one is R2. R3, like different distances to the different particles, right? Okay, the thing is not clear. I will draw it again. Okay, clear Madhu. Again, one iron. With the system in different way, that's show it clearly. That's right. Okay, and let's take this. Then there are particles. Because this is a rigid body. Let's say the rigid body is composed with a many number of particles. So I'm considering the particles on this body similar to the rotation of kinetic energy we thought, like this, rotating with the angular velocity omega. So each particle is having their uh, area. R1, R2, R3, like Rn, and this particle has a speed V1. This one has a speed V2, and this one has V3, V4, like that. Finally, this has Vn. One has Vn, right? Masses M1, M2, like uh, M. This one. So then you can write the total angular momentum of this system or the body. About the axis of rotation, right? That is sum of the angular momentum given by these individual particles. Right? It's you can say this as sigma MVR. MV is the linear momentum of a single particle, R is the distance. So that you can write sum of the angular momentum of individual, right? So here there's a so you can write the first particle has angular momentum, that is m1 r1 square, m1 r1 v1, m2 r2 v2, like this. All the momentum, angular momentum is gradient in Rn u. Now we can substitute for V, that is R1 omega. You write it down with me, right? Then take this common one and south. This is M1. R on this omega you can take out then. So this is the limit of inertia of the rigid body. Equal to sigma MIRI square. That's I is equal to 1 to M. So it is I. The angular momentum then you can write I equals L equals I omega. So then for a particle or a rigid body, you can use this equation, right? That's L equals I omega. You write it down and let me know after. Right. No, yeah, right, yeah. The direction of the angular momentum also we need to know that it can be taken obtained by using that right hand this corkscrew rule. Could you remember that right hand corkscrew rule you can use to find the direction of the angular momentum. Then convention is there. So that direction of the angular momentum direction of the angular momentum is given by right hand top screw. Remember, in your right hand, the fingers you curve to the direction of rotation. The thumb is directed towards the direction of the angular momentum. Angular momentum is axial vector. It's always along the axis. So here, let's say this rotate to this direction, then you use the right hand to the all the fingers curve to the other side except the thumb. The thumb is directed to this side. So the angular direction of the angular momentum is in this side, along the axis, right? Okay. Then let's see what is the relation between this angular momentum and the choke. Could you remember that the linear motion or the translational motion, the rate of change of the momentum, rate of change of linear momentum we discussed is at the force per Newton second law, right? In here also we can get the relation similar to that. Yeah. Here, okay. Right, then either topic as that's a relation between relation torque between torque and angular momentum. Angular momentum, right? Rho and L. All right. let's see then what is the relation between this angular momentum and the torque. Right then. So we know that this is a how we define angular momentum. That's angular momentum equals to the moment of linear momentum. But remember that's P into R. The P is the linear moment. Right. So by taking the rate of change of this angular momentum, right as a change in angular momentum, that's change in linear momentum into weight. And dividing it by time into R. Which delta L over delta T. You can write the delta P over delta T. What is delta P over? That is the rate of change of the linear momentum. It's a force experience on it. That using Newton's second law, we can say that is F into R. Right, that's I'm writing this reason means delta T, delta P over delta T, right? This using Newton's second law. And law of motion, right? They can write this F R. Then also we know that since this torque, that we are torque means that so it that's equals F R, the force into the perpendicular distance, right? So in tau equals F R, therefore we can write that tau equals this first equation and this second one, the first one and second one, you can say that the tau equals rate of change of the angular momentum. Similarly, that's this force equals rate of change of the linear momentum, and here similarly torque equals rate of change of the angular momentum. Okay, write it down. right? This equation you need to keep mind. You don't need to prove it, but if someone asks you to prove, you need to know how to prove it, right? And can directly use this. Then we can get another relation using this. So right this side, you already know that it's angular momentum. Angular momentum, let's see, equals to the I omega, right? This your question, right? It's I omega. So the change in angular momentum for a body or that psi is not changing, say that change in angular velocity. So when you consider about the rate of change of the angular, we are dividing this by delta t. You only can write that dividing by delta t. I that's delta omega over delta t. So what is this? As we mentioned before, that's this is tau. What is this thing? So this is the rate of change of the angular velocity. It is angular acceleration. So finally, its results, that's tau equals IL. So that's very important equation when you want to find the acceleration. This is similar to the F equals ma. So we call this equation, this is the rotational form of Newton's second law, right? Motion. How I'm saying that because tau relates to the force and moment of inertia relates to the mass and angular acceleration relates to the acceleration. So this is tau equals I alpha. This produces that tau equals I alpha and it's similar to the F equals ma. Okay, write it down. Write it down. This tau equals I alpha you can apply for any body it is in motion. You can find angular acceleration and the torque on it, right? If there is no torque applied on the body when it is moving, it's constant angular velocity. Write it down. හරිද? Okay. The right question. Right. That's a pulley, which is a rotating pulley, right? Pulley is rotating, and two mass and one each. So it's rotate, right? The mass of this part is then m. Also, this side is let's say this is m and this is 2m. And the mass of this pulley, let's say it is also m. The radius of the pulley, let's say r. When you release this, the pulley is rotating, right? It's rotating. Can you find that's what's happened actually? The pulley is rotate. When pulley is rotate, the section of the string that's A, B, and here this is C, D. The string A, B, and C, D has no same tension. It's the tension is different. So that's produce different tension. Question එක තියලා ලියාගන්න. හරිද? If the system release as shown in the figure, the system pulley system you can write one. If the pulley system is released, then find the first one tension of the strings that's A, B, and C. Third one, second one, that's acceleration of bodies. Okay, try to do this. Hello, let's see them. Right? How tension both sides are different. You need to keep in mind when the pulleys rotate, tension should be. Why the tension should be different? To rotate it, there should be the right. To rotate, there should be the torque on it. If the two tensions are equal, the resultant torque is zero. It will be zero. To make a resultant torque, there should be the when it is rotate, there should be the difference tension the both side. The different one, right? For my pen, if equal ma, I'm taking this is going down with the acceleration a, and this is going up with the acceleration a. I will use F equal ma here for the 2m mass downward. This weight is 2mg minus the tension is T2. That's equals to 2m the mass into A plus T. Then I use this equation for the simple m mass. It's moving up. That's T1 is upward force. Downward force is mg. And the mass is mn. Acceleration A. And another equation I will use then. Then for pulley, I use the tau equals IR. So rotate to this direction. Then let's see tau is T1 minus T2. T1 into R minus T2 into R. R is the distance is taken. I write the torque produced by T2 is T2 into R and torque minus the torque produced T1 is the opposite then minus T1 R. Yes, I is the pulley is taken and then given you that it should be taken as a uniform disk. If a disk is yeah, so the moment of inertia of a disk is half mr square, the mass of the pulley and radius r. And alpha, we know that alpha equals tangential acceleration divided by the radius, right? The a equals r alpha. Here the a alpha equals a over r. Then you can simplify the r common here and one r here, then cancel. So you can write the equation T2 minus T1, that's equals. That's MA over 2. So now this is easy to simplify this three equation and find this tension and the acceleration. You can do this. So automatically so T1, T2, the cancel. Then the 2mg minus mg, that's equals to the 2 ma plus ma over 2. Mm. And you can find that mg over. In using first equation, you can write G2 equals then 2mg minus 2ma, 2mg minus 2ma, no? Your first equation. So then A is 2mg over 7. Then 2mg over 7, let's go. Yeah, in A, this m cancel, sorry. G over 7 only. Yeah, G over 7. This is 10 mm over 7 is the tension of the 2. Let's say that T1 equals then MA plus MG. So A is so the 2 and V over C. Yeah, MG, right? The A here you substitute this value. And here there's a 9 MG divided by 7. That's how T1 and T2 find. Acceleration is also. Okay, right there. එයාගත්තනේ අය දාන්නව නම් කියන්න මොනවද මෙයාගේ ඉවරද හරි විතරක් ස්ටෝරිය නේද okay to finish the line හරිද? හරි. We discuss some more questions, but we've gone to the theory part first. Again, then write this principle of conservation of angular momentum. Principle of conservation of angular momentum. To remind us the linear momentum conservation, remember that there is no any force acted on the body. The moment, linear momentum the rate of change of the angular momentum is we define that it's a torque, right? If there is no torque applied on the system, the angular momentum should be conserved. So let's see that O equals delta L over delta. Small disconnection is there, right? So now it's okay, right? Let's write the principle of conservation of angular momentum. Momentum, right? So we know that the torque equals the rate of change of the angular momentum, right? So here, this torque means actually this torque is there is the external torque applied on the system. We consider here, right? Writing the torque, the V external torque applied on the unbalanced torque. So what's happened in this external torque is zero. It is zero. What's happened is rate of change of the angular momentum is also zero. So it's used to that change in angular momentum is zero. So change in angular momentum is zero means that is angular momentum of the body is not changed. It's not changing. It's constant. It's constant. It gives you that initial angular momentum that's equals to the final angular momentum of the system. So you can write that angular momentum is I omega. This I1 omega 1. Initially, that's I2 omega 2. It's final. So this is given by this angular momentum conservation. Yeah. Its advantage. If there is no any external torque applied to the system, its angular moment about this axis should be conserved. Okay, then write it as a principle and then after we write. Salam alaikum. First you write there. First I'll read it. Then Clearly, the total, yes, the total angular momentum, the total angular momentum of a system, total angular momentum of a system remains constant, provided no external torque acts on the system. Provided no external torque acts on the system. Oh, can you write this? You can write this initial angular momentum equals to the final angle. Right, write it down. ඒවාල ලියන් ඉවරනොත් මට මෙසේජ් එකක් දාන්න මම එතකම් බලන් ඉන්නවා. මොකද මේ මම මේක පැත්තට ගියොත් ඔයගොල්ලෝ ලියා ගන්න බැරි වෙනවනේ. Right. Now you know the angular velocity, angular momentum, angular then applied angular momentum and everything is there is applied. So then if you have given a torque on a body, right? If you given a torque on a body, that's making a rotation means it can do some work also. Let's see then how we can write the terms like this in rotational motion. That is work done by, we call it the rotational work done, and this the power delivered by the torque also. The two also you can see in terms of angular. So then we come to this applications of principle of conservation of angular momentum also. So this better you just explain about. You make applications to data. Right. Yeah, I have pretty small tutorials given you. Mm, let's see here. Small things there. Things like this, right? Yeah, the applications of conservation of angular momentum. Applications of applications of principle of conservation of angular momentum. Okay, let's try this. Okay, first one, right? That's planetary motion. Planetary motion around planetary motion around sun. We consider that planets are moving around a circular orbit, right? Mhm. Okay, then the sun is in the middle here. This is sun, right? So these are planets. The sun and the sun, the same orbit moving. They say this radius to this point is R1 and this is R2. This is moving around us. Planet, what's the sun is not at the middle. We know that the planets are moving in a elliptical orbit. Radius R1, right? Okay, at this position, let's say the speed of the planet is V2, and this position, let's say it has a speed V1. So here it's a motion, but the axis passes through the sun. So this direction is the angular velocity omega. Okay, this is the path of its motion. That's how it's conserve this angular. When this object or the planets are moving, is there any torque applied on it? There is no torque applied on it. Because that's a forces acted on these planets are gravitational force on it. There's a gravitational pulley directed toward the sun. So then there's no other forces acted on it to make a torque. So then torque is zero. If torque is zero, the angular momentum should be conserved. Right? So, you write there. In planetary motion, in planetary motion, in planetary motion, the gravitational force is gravitational force. Within bracket write the centripetal force. Gravitational force, the centripetal force always passes through the axis of rotation. Passes through the axis of rotation. Axis of rotation. So its moments of force is zero. So its moment of force is zero. Moment of force is zero. So you can write that means there's no torque on the planet. That means there is no torque on the planet. No torque on the planet, right? Right, and therefore, therefore, the angular momentum of the orbiting planet, therefore, the angular momentum of the orbiting planet remains constant. Remains constant. Right? Right? If V1 and V2 are the speeds of the planet, if V1 and V2 are the speeds of planet, when it is at distances R1 and R2 respective, speed of planet when is at distances R1 and R2 respective, right? perspective. Then you can draw this one and write this. Since external torque is zero, that's the initial angular momentum equals to the final angular momentum. The initial angular momentum is V1 position, that is a mass. That's V1 R1. MVR, linear momentum MV and R1. Finally, same V2 R2. So then cancel out. So V1 R1 equals then V2 R2. You can write due to the angular momentum conservation. So when the planetary motion is, well, obviously angular momentum conservation. Write it down, the first application. എന്തൊക്കെയാണ് article ചെയ്യാൻ വേണ്ടത്? Right. Right. In for planetary motion, I will discuss this in a little bit further. Here you can see how this velocity, this speed. Let's say that when taking a small change in this area, like small change in this area, I'm considering as A1 here. A2, let's say 2. This time taken from here to here, let's say delta T. Area changing delta A. So then the speed you can write, the speed is that's speed proportional to the rate of changing area. How I write this then, this distance you can write as writing this uh, S R. That's d equals delta S over delta T. So delta S you can write that's R theta, R into delta theta like that. You can write R theta, so into delta T like. And then this corresponds delta, that's R into delta S. This is that's area of a circle is pi r square. The area of a that's section. The section area this angle. We can write it in radian. For a 2 pi, it's pi r square. So how much is for this angle like that? එහෙම තියලා ගත්තා finally එන්නේ මෙන්න මේ equal time එකකදී just sweep කරන area equal කියලා. දැන් මෙතනට යන්නේ delta t නම් control name of just let's call the Kepler's the second law. Kepler's second law is given that what up here? It's a second application. Second application, right? Make a put a experimental number. Oh, second one. I'll explain it first and then right. I will share you the file, right? Can you see the board? Their name is
Yes, sir.
right. මේක මම මේ ඔයගලන්ට අද දෙන්න කියලා හිතන් ඉතින් දැන් මම මේක ඔයගලන්ට මේ දැන් මොකද මේ ඇප්ලිකේෂන්ස් හැම ගොඩාක් ඒවා ලියන්න ගියාම වෙලා යන හින්දා මම මේක ඇප්ලිකේෂන් එක මොකක්ද කියලා එක්ස් මොකද මේ රූපේ එහෙම අදින්න ගියාම it's difficult නේ ඒක හැර this is theory part already we discussed and this application the planetary motion application also we discussed other one is just explaining volunteer right this one if there's a child right on a chair the chair can be rotated right and there's two dumbbells or the masses on his hand and then we can make a rotation and release. So then without the friction, it rotates. If we ask this child, picture, what's happened in this situation or the first case, having larger moment of inertia, because there's a mass is distributed away from this axis of rotation. So its moment of inertia is larger. In the second picture, if we bring the masses towards his body, moment of inertia get lower, so it reduces. And when he takes the arms towards his body, there's no torque applied on the system, right? There's no applied the torque. So what's happened in called the conservation of linear moments, angular momentum. To conserve the angular momentum, then if the moment of inertia reduces, angular velocity should be increasing. So then we can observe that in this second picture, the situation, it's rotate with the high speed than the first one. So that's also right as I1 I omega I equals to the IF omega. So then if IF is less than I because it's take hands towards him, so then omega F should be greater. And similarly, we can explain about this ice skater also. When he extend his hands and rotates, it has a small angular speed. If she takes hands towards his body, then it's rotate with high speed. And here also another one point we need to take this angular, the rotational kinetic energy a little bit increase here. How that energy increase? Because that's to increase the energy, we need to do some work. No? So, that's when you bring this weight towards the body, you need to apply the force on it and take it. So then you need to do some work on it. So that work done is stored as a kinetic energy. That's how it rotates faster also. And this springboard drivers also you can see here that's when they swimming, this kind of stance they taken during the motion, diving, right? Initially the hands and legs are extended and then they take the hands and legs towards the body. So here it's as a higher, larger, it's a moment of inertia. So small rotation, the rotational speed is smaller. And then we can take a larger rotational motion by taking the hands towards the body and increase the angular, the moment of inertia, right? And again, it's raised to the water. Then he see that extends hands and legs to reduce the angular velocity. Right, angular velocity reduce, so then can take the very clear diving. The long jumping also you can see here. That's when they jump, is some places their body is extended, and some places take their hands and body towards the body shapes and making that's according to this, he can reduce the angular momentum. Sorry, keep the angular momentum conserved by changing the moment of inertia, and then you can increase the angular velocity. Because then in the landing case, we need to remove the angular, because if you want to take the larger jump, large distance, that larger linear velocity should be done. So that's how he extend these hands and legs and reduce the angular, sorry, increase the moment of inertia, and then he can get linear speed greater, linear speed, and linear is most. And when it comes down, then it's all the legs and the arms take towards the body, and then you can jump, take a long jump. So by taking small things like that, you can uh, take a larger distance. Okay, here this sixth one, I'll explain it in later. Right, later means that this one is different with others. Here, it shows you that's the direction of angular. I'll let you know. I think that's do you want to write this all? Oh, is it enough? I've given this handout. කියන්න handout එක දුන්නා නම් ඇතිදනේ. ඔය ඔක්කොම එකම විදිහට explain කරන්න කියන්නේ. තව මම මේකේ නැති එකක් තව එකක් explain කරන්නම්. හරි. මේක මම දෙන්නම් ඔයගලන්ට. ඕකේ නැත්නම් මේ ඔක්කොම ලියන්න නිකන් ඔක්කොම වැඩි. ඔක්කොම වැඩි කියන්නේ ගොඩක් ලියන්න මම මේක explain කරලා කියන දේ ඔයගොල්ලෝ ඒක බලන්න. මම මෙන්න මේක explain කරනවා. In here That's also the person is on the rotating chair, right? The turnable table like that. And we given a wheel which is rotating, right? When this wheel rotating, its angular momentum is upward. You can see that's a V WH we put there. That's angular momentum which is upward because it's rotation to this direction, right? So then nothing happened because initially the wheel has the angular momentum upward, and also when you given this wheel to the hand on the person, also the angular momentum is upward. So then nothing changed, right? And if we ask to change this direction of this angular momentum of the wheel, that's by uh, turning down the hand, right? Can upside down, then this can change the direction of the angular momentum down. Angular momentum is not changed here, right? That the direction of the angular momentum is changed, but without applying any torque. But you can't change the angular momentum without given the torque on it. So then what's happened here? That then now the angular momentum is downward. That's why I'm put minus. But initially the angular momentum should be upward. To make the angular momentum in upward as initial, but the system will rotate about the axis of this rotation to make the angular momentum upward. Like that, LB is the angular momentum upward. Right? That will happen automatically. If we make a haro program, yeah, system එකත් එක්ක අනිත් පැත්තට කැරකෙන්න ගන්න. Right? So we can write the equation like this thing. According to this law of conservation of angular momentum, we can see here the angular momentum, initial angular momentum of the wheel, initial plus the initial angular momentum of the man plus chair. That's equals to the final angular momentum of the wheel plus final angular momentum of the man plus chair. And initially it is taken as LWH. Initially there's no angular momentum for the man and the chair, it's stationary, right? Finally, this angular momentum of the wheel is minus L because this direction is changed. And finally, the system has LB, let's say then the LB, the angular momentum of the system, you can write that is 2 times of the angular momentum of the wheel initially. So this will happen, right? View of the application with explanation, right? Then කවුරු ඇහුවොත් එහෙනම් දැන් අවම ඉන්න මනුස්සයාට හරි okay මම ඉන්නවනේ this tenable table එක අවම ඉන්න මනුස්සය හරි දැන් කොහොම මනුස්සයෙක් වෙන අපි දෙනවා wheel එකක් මේ විදියට. Now this wheel is given, this man can hold the wheel like this. It's rotating this plane, right? Then also nothing happened when you given the wheel. But if you ask this person to turn it little, right? If this man turn the wheel like this, let's say. And then horizontal debate, පොඩ්ඩක් turn කරනවා මේ පැත්තට නිකන් හරි. Wheel එක is rotating about this. මොකද වෙන්නේ? දැන් initially angular momentum එක තිබ්බේ මේ පැත්තට. මේ axis එක දිගේ කොහොම තිබ්බේ? මේක මෙහෙට rotate වෙද්දී ඇත්තටම direction එක තිබ්බේ මේ ඇතුල් පැත්තට. මේ පැත්ත. දැන් මෙයා පොඩ්ඩක් මේක හරවපු ගමන් angular momentum එක යනවා පල්ලෙහාට. දැන් horizontal තිබ්බේ පොඩ්ඩක් මෙහෙම මේ පැත්තට හැරෙනවා. මෙහෙම හැරෙනවානේ මේ පැත්තට. හරි. So there's a component to this direction and vertically down component එකකුත් එනවා. Otherwise Ly and Lx is the component of this L. So initially angular momentum තිබ්බනේ horizontally, it's not changed, but there's no angular momentum in downward. So then to rebalance this downward angular momentum, the system will rotate to produce the angular momentum upward. මේ පැත්තට එන්න එකක් කරකෙනවා LW. දැන් මොකද වෙන්නේ මේ සිස්ටම් එක angular momentum උඩට එන්න මේ පැත්තට කරේ. ඒ කියන්නේ අපි මේක මේට හැරෙව්වොත් wheel එක මේ පැත්තට හැරෙව්වොත් මේක මෙහෙට කැරකෙනවා. wheel එක අපි අනිත් downward හැරෙව්වොත් මේක අනිත් පැත්තට කැරකෙනවා. This thing really happened, right? දැන් ඔය අර hand out එකේ නැති application එකක් ලියමු. මේකත් මතක තියාගන්න මෙහෙම වෙන්නේ කියන්නේ කීපයක් තියෙනවා. ඉතින් අපේ application එක ඔතන එකයි නේද? second කියලා දාන ලියන්න අර hand out එකේ ටික වෙනම. එතන ලියන්න එහෙම let's see consider නිකන් අඳින්නම්. ඉතින් මේක දැන් පොඩි මූලක් එතන විදිහට මෙහෙම කට ගන්නවා. මේක අපෙන් කැරකුවොත් මේක මේ වගේ large. අර එතෙන්නේ මෙහෙම. එකක් හිතමු. Initially it's at the angular momentum rotates this direction. This angular momentum of the initially it's as the r I the radius and මේක මෙහෙම එන්නේ අඩු වෙලා. එතනදී r f වෙනවා කියලා හිතමු. පේන්නේ නැහැ නේ හරිද? මෙතන ඉඳන් මේක තියෙන මේක මෙතන ඉඳන් මෙතන t equals 0 it's here and t equals t මේක rotate වෙන මෙතනදී the radius of this bar is rx. DNA දෙපිච් එක මේක නිකන් ලණුවක් පිට කාලා මෙහෙම කරකවනවා. මෙහෙම කැරකි මෙතනට එද්දී initial moment of inertia අඩු වෙන හින්දා speed එක වැඩි වෙනවා. the unit phase that is now. Force is towards this direction only. Right. So it's rotating in this circular path. So මෙහෙම ලියන්න ඊට පස්සේ අපි මේක අඳගමු. So right, consider a device shown in the figure. Device shown in the figure. Right, shown in figure in which a small body attached with the string with the string by the stability string is rotating initially in a circle of radius r1. Ri, right? Radius Ri, right, with angular velocity omega I. Right, the free end of the string is pulled down. මෙතන string එක මේක hole එකක් දාලා මෙතන පල්ලෙහාට ඇද්දොත් යාගේ ස්පීඩ් එක ඒත් වැඩි වෙනවා. මේක කරකවන්න පුළුවන් අතින් නැත්නම් just pull down. Let's say string is pulled down, right? String is pulled down and so body moves on. A circle of smaller radius. Alright. Right as RF is less than RI. Udah, sudah mat. Hari, smaller radius. If you pull down this string here, that's taking this what the case we can consider. If you pull down this, right, this string, the string passes through this hole here, and if you pull down, the radius reduces and the other way that if you use this string, that's wrap around the cylinder, also the same thing happen, right? So next one I will write that one. Here you can write this one, smaller radius RF. So then what happened then? So you can write as you need to explain this if someone asks you to explain with the help of linear the angular momentum conservation, you need to write in this way, right? As the torque, we need to say that if there's no torque, because if there's a torque, we cannot say like this. As the torque of force capital F is 0, it's about the axis of or the axis of rotation. So the angular momentum of the body remains constant. And here we can cite this I omega that's equals to I omega f. It should remain same. This IF means in the particle of mass m, let's say, how can I write this system? When you are taking this, in here also you can write this velocity of this one is Vi here. And finally, when you storing back there and writing, the speed is then V f here. So I you can write the same Ri square. Omega you can write as Vi divided by Ri. And If you can write M Rf square. And the omega if you can write as Vf divided by Rf. So then M cancel, then R1, Ri, Rf, Rf cancel here. Then finally Vi, Ri that's equal to Vf, Rf. Same like result you can obtain. You can draw it and write it down there. This motion you can write that's kinetic energy also increase in this system, right? Am I right in this system? Increasing kinetic energy due to this. So you can write as final kinetic energy minus initial kinetic. So we can write this final kinetic energy that's a rotation kinetic energy IF omega F square minus half I omega I square. Half we can take out. I the moment of inertia that's M R F square. So also we can write VI RF VF that's square of that minus half we take out, that is M R I square VI square over R I square. V over R is square of that, right? So R cancel, you can see here then half M VF square minus VI square. This is related to the that's linear kinetic energy of translation motion. You say you can write this. You need to keep that in when you get from the system. If it changes without changing the angular momentum. So if you do some physical changes there, angular momentum remains same and the kinetic energy but changes. You write it down and let me know if finished. Right. So, did you get an idea? Right. අපි example එකක් කරලා බලමු දැන් ඔය. Angular momentum conservation apply වෙන example එකක්. හරි. To write down the example I'm giving you, right? Write down the example. Consider a disk of mass. Consider a disk of mass capital M. Consider a disk of mass capital M and radius capital R. R is rotating with angular velocity omega. Omega, that's about its geometrical, that is geometrical axis as shown. Look at the figure, right? They write a small object of mass symbol M falls gently on the edge of the disk and stick to it. Right as fine the angular velocity and then the angular velocity of the disk. Here the disk is like this, right? Disk here. The disk here. It's rotating about the axis, the angular velocity omega, and its mass is M, and the radius is given as R. Now the small objects, this is a before system, right? So the small objects is stick on each edge. Let's see, edge stick there. Small object that has a mass mg. And then the moment of inertia of this system is changed. Let's see, omega will be omega dash. But the angular momentum should be constant because no torque applied on it. Now you can find this omega dash. Find one, but දවල් ගහන්න පටන් ගත්ත එක තමම වහිනවා මෙහෙට. ඕගොල්ලන්ට පැත්තට වහිනවද? ඒ විදිහම වයින් ආවනම් නාන්න වෙනවා යන්නෙත් නාන්න වෙනවා එද්දිත් නාන්න. ඔක හදන්න මේ මං අර මේ හෑන්ඩ් අවුට් එක මේ ගෲප් එකට දාලා තිබ්බා කෝකටත් ඔයාලට නිකන් බලා ගන්න හරි ඉපේ මේ මං ඒක print out එක දෙනයි ඉන්නකල ක්ලාස් එකේදී ඔයගොල්ලෝ නිකන් කියවලා හරි බලා ගන්න ඒ ටික. ඒතර ඇප්ලිකේෂන්ස් ටික හරි ගෲප් එකට ඒ හින්දා දැන් Hi, let's see how we can do, right? Now, the moment of inertia of this disk is what? Let's say it is I1, it's equals to the half this capital M R square. It's a disk. And moment of inertia of the second system is then that's it. Moment of inertia of the disk will not be changed, but another mass is attached to there. That's it's at the distance R. Here then it is it's moment of inertia mr square, right? Now, as the angular momentum is not changed because no torque applied on it, you can say that since the external torque is zero, we can write that the initial angular momentum equals final angular momentum. That's I1 omega 1 equals I2 omega 2. Then I1 is the half mr square. Omega is given as the angular velocity, and final angular momentum is half m r square plus simple m r square and omega dash m. And then omega dash, you can write this simply, you can simplify this easily. Then r square will cancel. Then it is yeah, m omega divided by m plus simple to. So this is English. Is it clear? හරිද? And also, there are some phenomena, right? If you finish the writing, let me know then. నేను ఇవ్వడానికి అని మైతోటి right? Mm, the other thing is that there are some phenomena which we can give as angular momentum. Yes, here the idea is then what if there's no torque applied on it, the angular momentum will not be changed. That means if you given the rotation and send the body, like say, if you consider was a bullet, right? The bullet, when you firing the bullet, let's say you make a rotation and then fire, what's happened then? It tries to keep the angle direction of the angular momentum the same direction because there's no torque applied on it, right? If you send a bullet without the rotation, right, without rotation, let's say it's just moving like a projectile and then hits on the ground. But when you given the rotation, what happened then? It's move more distance and then turn back like this. Because of the angular momentum is there. So angular momentum, direction of the angular momentum will not be changed uh, without any torque applied on it. So it's more distance thing. And also just in a coconut, when you coconut all the coconut. So given any rotation to the coconut and then the coconut will come down and hits the ground without any rotation, it hits the ground. Of this the backside of the coconut because then the coconut will not be break out. If you send it without rotation, it will moving like a rotation and then they hit on the ground. It's some part of the top of the coconut, then it can be break out. And also there's a rugger players. Also they make a rugger ball. When they send the rugger ball to another player, they make a small rotation and send. So then the other player can catch it at the same level. If not, it's more like a projectile and go down. And spinning really, that's very many phenomena we can describe like this. So thus all the phenomena also given you in that handout too, right? You go through them. Here the phenomena is then angular impulse. We call that the angular momentum multiplied by the time. The angular momentum because torque multiplied by the time with the torque applied. So it's equal to change in angular momentum, right? So if there's no torque, the angular momentum will not be changed then. So these are some practical phenomena applications about this. The bicycle also, you know that when the bicycle is not rotating, the wheels are not rotating, it's fall down. But when it's rotating, you can make it in equilibrium. And spinning of this top also, you can spin the top. It can make a rotation like this and we can be in equilibrium. But if there's no rotation, it fall down. And the bullet is also there's something number this sky view and this coconut one and also this rubber ball throwing also we make a rotation and send it. And this helicopter rotor also you can see. When this helicopter blade is rotating, to conserve the momentum, what should happen is the helicopter body will move to the other side. It's rotate to the other side. To avoid that rotation, that's a small rotor blade you can see at the end of that's a tail blade we call it, end of this helicopter. That's a small fan-like thing. So it rotate and they maintain, they avoid the rotation of the body then, and then keep it in motion. That's rotor blade is used to turn the vehicle also, turn the helicopter also. If you want to turn some, then let's say in the right one, දකුණට හරවන්න ඕන නම් අපි මේ rotor blade එකේ speed එක වැඩි කරනවා. rotor blade එකකින් එන torque එකකින් හින්දා එයා මේ පැත්තට හැරෙනවා. අඩු කරොත් අනිත් පැත්තට හැරෙනවා. ඒ කියන්නේ මේක balance එකේ තියෙද්දි තමයි without any direction is turn, it's moves forward. Similarly, these are the some phenomena related to these things, and also you can go through the also question I'm given you in this practice questions. You can see here in the tutorial there are so many questions there, right? That question we did now. This one I forgot about it. It's in the tutorial. So you go through the also go to questions, right? So I'll explain in next day. There are 13 questions here. Another tutorial I'll give you. Is it clear? Is it clear about the tutor? You can go through it and then
Yes,
wait.
sir.
Another two small terms we need to discuss. I'll discuss that one and stop the class, right? That is rotational work done. First one, write that rotational work. Because then this theoretical terms parts is finished. Then next day we will discuss about the final part of this rotational motion, and then after we discuss the circular motion. Right, rotational work. Rotational work actually is done by the torque. Force එකක් දාලා කරනවා වගේ torque එකක්. If you given a torque on the body, you can do work on it. Right? Here, this is a plane there, and an object I place. This is axis. Let's see, by applying, if we rotate this body to this direction, right? So then axis is changed by the distance, let's say delta S. I'm making an angle theta here. Okay. To turn the body to there, you need to apply the force on it. Let's see, they apply the force on it. They apply the force on it. Let's say it's safe. Under this force is turn delta S, let's say, right? මේක ඇඳ ගන්න කොහොමද? ඊට පස්සේ අපි ලියමු. Can draw this. This force actually is applied perpendicular to this line, right? You can draw it. එතකොට මොකද මේ මම පොඩක් ටික වෙනස් කරලා ආතන එක පැහැදිලි. Okay, I'll draw it like this. වෙන color එකක්. Let's see them under the force. This body turning to this position. Let's see this red color one. From here to here, we apply the force to this direction. This, under this force is turned with the angle theta, right? And the distance traveled during this is, let's say, S, delta S. The force applied on this to turn it, right? Now, right, like this. The distance to this force applied from the axis of rotation, let's say it is R. Now we draw and mark it. So we consider here, consider our body subjected to a force capital F. Suppose the body undergoes an angular displacement delta theta due to torque. Of course, like, so then we can write as work done. That work done we generally define as the force multiplied by the displacement, right? This angle you can write delta theta. And then this work done delta W, let's say it's equals to that force, the displacement is delta S. And this cos, the delta S you can write it R delta theta. Because S equals R theta, you know. Alright, right? This is R times delta theta. This S equals R theta, you can apply here, right? I'll write in there delta S equals then R delta theta. So here then you can say this F into R, it's a torque delta. So it's equals to torque. This is W, not omega, right? Work done and delta T. So here for a larger scale, you can tau theta. So rotational work done is then R omega. That's W equals tau theta. This is the work done, right? That's the angle multiplied by the torque. Right. Plus, then right, that's the power divided by the torque. Same by right, the power delivered by torque. That's the work done. You can write as rho delta theta. Dividing it by time is the power then. Rate of work done is the power. That is tau delta theta divided by delta t. This is the power there. So this is the rate of the angular displacement is the angular velocity. So then power is tau. Here this power equals to the tau multiplied by angular velocity. Clear? So this is the power. Power what normally under the nature. Okay, you finish your writing and I will stop the class from this point today. හරිනේ. දැන් අපි ඉස්සරට කියන ඊළඟට කරමු ආයේ ඔත් එකේ ගණන් ටිකක් හදාගෙන ඉමු. හරි. හරි දෙන්න.
Thank you, sir.
හරි. නෑ පුතා.